So how do we simplify the first one? Yeah, 4 times 2, and then? Right, so the square root of 4 becomes 2, and the other 2 remain. Right? So that's it. How about the next one? Right, 25 times 3. Actually, turn my phone off. Yeah, so that's 5 square roots of 3. Right. Good. How about rationalizing the denominator? Remember the nice case when it's just the 1. So what do we do? By what? Square root of 3 over square root of 3. So that becomes 3. Right, that becomes 3. So I can cancel the 3's. Square root of 3. Right? And how about the last one? You want to do the opposite sign, right? We do the conjugates because we want to do the difference of squares formula, right? So that allows us to, square. You always do the opposite because that will give you the, well, no, because if you do the negative sign, then you don't even get anything pretty in the denominator. It will come out, yeah. Well, I mean, you'll end up with, you'll end up with 5 plus 3 is 8 minus 2 square roots of 15 in the denominator. If you multiply by the same thing, it'll get messy. But if you do the conjugate, it always cancels the square root. That's okay. I'll take a whole bunch of points off for that one. But if you didn't reduce it over here, I'm okay. I mean, the big thing here was to do the conjugate. But it's 1 problem out of 4 on a 5-point quiz. So, I mean, you're not going to, you won't suffer all that much. What? You're late for it, yeah. Now, I actually want to say something about this problem right here. The 3 and the square root of 3. There's another kind of a sneaky way of doing that problem. Because 3 and the square root of 3, there is a relationship between those two numbers, right? They both share a 3. I can always think of that numerator, the square root of 3. I'm sorry, the numerator is 3 right now, right? Well, 3 is the same as square root of 3 squared. Do you agree with that? 3 is the same as square root of 3 squared? That's okay. But do you agree that these are equivalent statements? Well, then I can just use the rules of exponents and cancel one of the square roots of 3, and I'm left with the square root of 3. I still get the same answer. Right, I'm just using the rules of exponents here. I have the same base, which is square root of 3, and then I just subtract powers, 2 minus 1. But it only works if they share the same. I mean, if I had 4 in the numerator, then it won't work. You have to go through the process. But it just happened to match, so we can kind of sneak in there. All right, so homework questions. You got homework questions? Yeah? Like that? Okay. Is it? All right. So using rules of square roots, we have a product of 2 square roots. I can always make it as a 1 square root of a product. That's legal, right? Well, 0.1 times 10. What is 0.1 times 10? 1. So that's same as the square root of 1, which is 1, right? So those problems you just have to manipulate with that rule. Whether you have a product of two square roots, you can make it into a single square root, or a single square root of a product that can be split into products of square roots. I'm not sure. What does that say?
Square root of 45 times the square root of 5.
Yeah, because you cannot compute them separately, but if you pull them together, that becomes 45 times 5 under the square root. And 45 times 5 is 225, which is a perfect square. 15, right? There's another way you can do this problem. 45 is the same as 9 times 5, right? And so you can do square root of 9. So that's 3 square roots of 5 times square root of 5, right? You can take the square root of 9, becomes 3. So here you have 3 times square root of 5 times square root of 5, which is same as 3 times square root of 5 squared, right? You have 2 square roots. So what is the square root of 5 squared? 5. So this is 3 times 5, which is still 15. Now, it worked this way because you're ending up with identical radical, which is easy to compute. But this is more standard way. Just push them together, end up with a perfect square, and then take the square root. Yes? Uh-huh. What does it say? Under the same square root? Oh, okay, yeah. 457 squared minus 84 squared, still under the same, like that? Or is it one big square root? One big square root. Okay. So this is kind of that question that I picked on you on that worksheet 18. And in your notes, we did go over some of that in class, that you cannot just drop all the squares. Doesn't work like that. You have to turn minuses into products. And that's difference of squares formula. So you have to use the difference of squares formula, which give you 149 minus 76 times 149 plus 76, right? And the same thing in the denominator, 457 minus 384 and 457 plus 384. Okay? Is that all right? Just using the difference of squares. Well, now I have to compute each individual parenthesis. So 149 minus 76, what's that? 73, which is kind of an awful number to have under the square root, but maybe good things will happen eventually. Now 149 plus 76 looks like 225-ish. Is that right? Now 457 minus 384, I'm just wild guessing, equals 73. Otherwise this problem would just suck, right? And 457 plus 384 is 841. All right, so 73 is canceled. So that's a good news. And all right, so I'm left with the square root of 225 over 841. Right? So square root of 225, I believe, is 15. We can do that. And the square root of 841 is probably 29. Is that right? Yes? So that's it. Is that okay? Now, do you know how I was making that guess that it's probably 29? Well, because you know it's less than 30, because 30 gives you 900. And then one thing you should always look at the last digit. Last digit is 1. What? Well, it could be 1 or 9. That's right. Because 9 squared ends up 81, so it ends up with a 1 in the end. Or anything with 1 in the end ends up with a 1 in the end. So your options were really 21 or 29. And you know 21 is way small. So, well, of course you could just use a calculator. But yeah, you can think about this. You can look at the last digit and then think about which number squared end up with that last digit. So 9 squared has 1 in the end. 1 squared has 1 in the end. And I think that's it, right? If you square any other number, you don't get 1 in the end. I mean, just from 1 through 9. I think, Nicole, yeah? Yes. Yeah. What does E say? 108 over square root of 12? Like that? Okay, well, I'm pretty sure you should be able to reduce this somehow. Oh, don't get decimals. Yeah, because 9, period? Yeah, this reduces into just 9, right? So that's a square root of 9, so that's 3. See, what you ended up, you told me 6 square roots of 3 over 2 square roots of 3. Well, that cancels and that gives you 3. You still get the same answer, but you went really the hard way. Yeah, but yeah, if it's under the radical, reduce first and then see what happens. 1f, what does that say? Square root of what? 1. Oh, and 7 ninths? Under the same radical? Times 4/25? Like that? Okay, so the big thing here is to convert 1/7/9 into improper fraction. And then when we do that, it's a denominator, yeah, times the whole plus the numerator. So 9 times 1 is 9, plus 7 is 16. So 16 ninths times 4/25. Right? Which are 4 perfect squares. Right? They're all perfect squares now. So you just take square root of each. The rules allow us to do that. So it's 4/3 times 2/5. So that ends up with 8/15. Just multiply straight across. So if you have those mixed fractions, convert them to improper fraction. Yeah? And what does that say? Like that? So we're using your favorite formula here. That's okay. This one is messy. But the big thing here is to realize that this is your a squared plus 2 times a times b plus b squared formula, right? This is your square root of some formula. So that's the big thing, okay? Now, next is just to computing those. So I'm squaring 7 square roots of 3. So I have to square 7. What is that? 49. And I have to square the square root of 3. And what is that? 3. So 7 turns to 49, and the square root of 3 turns to 3. And we can do that because it's a product. We're squaring a product, so we're squaring each individual item in there. Plus, over here, I'm just going to look at the coefficients. 2, 7, and a 2. 2 times 7 times 2. That's 28. And the square root of 3 and the square root of 5, that's a product. So I can pull them together. That gives me square root of 15. So I'll multiply 3 and 5. Because again, that's a product. You can do whatever you want with a product. They're nothing. The sums, those are tricky. And then the last one, you square the 2. So that's a 4. And you square the square root of 5. 5. So then, just 49 times 3 is 147 plus 2. Was that right? Square root of 15 plus 20. Right, so 167 plus 28 square roots of 15. Yeah. So I multiplied the constants, 2, 7, and 2. So 2 times 7 is 14, times 2 is 28. And then you combine the two square roots together. 3 times 5 is 15. So again, this shows you if you take an ugly number like that and you simply square it, you end up with another ugly number. So that goes to rationalize the denominator. If that was in the denominator, instead of squaring it, you would multiply by the conjugate. And you'll just end up with 147 minus 20, which is no radicals left. Right? Yes. Good. Let's learn. I don't know if we have time for that now. I'll go super fast. So I'm going to hit about 4 brand new topics right now, but they're kind of small topics. They're just putting everything together. So we understand how to square things and we understand how to square root things, right? We know these two. They relate to each other. But then if we take it further, if you can cube something, then you should be able to take a cube root of something. And if you can raise something to the power of 5, you can take a 5th root of something. You can reverse those exponents. So we're introducing the nth root. Yes. Nth root. So again, if you understand the square root, you're probably going to get the nth root pretty well. So again, the definition, the nth root of a equals b implies if you raise b to the power n, you're going to get a. So the a, we call that a radicand. And that little n on the top, that's the index of the radical. So if it's a square root, we don't write anything. It implies, radicand. It implies 2, but any other power will have a number there. So cube root, 4th root, and so forth. I'm just going to hit you with a few examples. Let's say a cube root of 8, 2. Very good. Because if you cube 2, you get 8. So again, using the definition, 2 cubed equals 8. Does that make sense? If I take a cube root of 27, 3. Because 3 cubed is 27. Is that okay? If I take a cube root of 54, well, 54 is 2 times 27, right? 54 is 27 times 2, and I can take cube root of 27. That's 3. But 2 doesn't go anywhere, so we can do similar operations as we did with square roots. With higher roots, you can extract a perfect cube if it's a multiple of a number. Is that okay? What? Just stay with 27, is that what you? Yeah, you know that's not going to happen. So it's a, but again, but you get the idea, right? If I ask you that question, 2, because 2 to the power 4 equals 16, right? Because again, 2 to the power 4 equals 16. Okay? Now also, if you recall, if I ask you what is the square root of -4, you will say, right, not a real number. Same thing goes with any even root. If I ask you what is the 4th root of -81, you will still say you cannot do that, because anything to the power of 4 comes out positive, right? Because it's an even power. So here I'm asking what number raised to an even power comes out -81. So again, we don't know numbers like that, so not a real number. But with odd radicals, if I ask you what is the cube root of -8, that we can do, because cubing negative numbers ends up negative. So actually the answer here would be -2. Because if you take -2 and you cube it, you'll get -8, right? So you can get negative answers with odd radicals. How's that? Oh, come on, not that often. Yes. Because if I cube a negative number, it comes out negative, right? But if I raise a negative number to the power 4, it will always come out positive. Because that has to do with the even powers or odd powers. Even powers always positive, right? Any number to an even power comes out positive, right? While with odd powers, positive number to an odd power is positive, negative number to an odd power is negative. So therefore, we can reverse negative numbers with odd radicals. Does that make sense? Okay. All right, good. So again, they will come up. We're not going to take him to the same extent that we did square roots, but just be aware there are higher radicals. You'll see them. So moving on, rules of exponents. Let's review the rules of exponents that you know, and we'll add up to them. So review. Rules of exponents. So let A and B be real numbers. Let M and N be natural numbers. So far, I think you know about 6 rules of exponents at this point. We know if you take 2 exponential expressions like that have the same base, a to the power n times a to the power m, what do we do with exponents? You add them, right? So that becomes a to the power n plus m. Now, what do you do with exponents when you divide? You subtract them. So it's a to the power n minus m. And the third big rule, if you take an exponential expression and you raise it to another power, what do we do with exponents then? Multiply them. So it's a to the power n times n. Right? You know these 3. You know these 2, we've been using them extensively. If you have a product and you raise a product to the power, you can distribute it like that. You've seen me do that earlier today on some of the homework questions. And the same thing goes for the division. If you have a fraction raised to the power n, that's a to the n over b to the n. Right? We've seen that. And another rule that I think you know is a raised to the power 0. 1. So anything to the power 0 equals 1 as long as a is not 0 itself. Okay? So you know this 6. We're going to add about 4 more today. We're going to have 10 rules of exponent. Lovely. All right, you ready? I'm going to start with this example. 2 to the power 5 divided by 2 to the power 7. So it's a division, same base. If I go back to my rules of exponents, which rule am I going to use? The second one, right? But look at the second rule. It tells me just take the exponents and subtract them. Which means, in this example, what am I getting in the exponent? -2. So the fact that we can subtract exponents leaves room for negative powers, right? So you can end up with a negative exponent. Now what that really means is this. Because I can take an alternative route to this problem. I can rewrite it as 2 to the power 5 over 2 to the power 7 like that, right? Can we reduce that fraction? So that's gone, and that's 2, right? So what's left in the numerator? 1 over 2 squared. So that's the same as that. So negative exponents are reciprocals. Okay, so that's what negative exponents do. They put that expression. Yeah. So basically the new rule is, so that's rule number 7, that a to the power negative n is the same as 1 over a to the n. So negative exponents are reciprocals. In general, I can make this rule, rule number 8. If I have a fraction raised to a negative power like that, again, negative exponents are reciprocal, so all it's going to do is going to flip the fraction. It's going to become b over a to the power n. So negative exponent just flips the fraction. Okay? So a few more examples using these rules. So how about 5 to the negative second power? Can we do something about that? By the way, we really don't like having negative exponents in our answers. It seems to be we should be able to get rid of that. So 5 to the negative second power is the same as 1 over 5 squared. So just flips the number, so that's same as 1 over 25. Is that okay? So that's all we have to remember. The negative exponents are reciprocals. If I give you something like this, 2/3 to the power -3, so it's 3/2 to the power +3, so that's 27 over 8, right? How about 1/2 to the negative second power? Yeah, so just flip the 1/2, that becomes 2 squared, so that's 4. Okay? So again, negative exponent just flips the fraction. Are you okay with that? But what if I write something like this? 1/2 to the negative second power. So only denominator has a negative exponent. Well, yeah. Well, first of all, these two problems are identical. If I use my other rule of exponent, where I just distribute the power, 1 to any power is 1, and 2 to the negative power is equal to the negative power. So really, these two are the same. But what we can say, actually, if you see a negative exponent in the denominator, that'll just become a positive exponent in the numerator. That whole thing will just become 2 squared again equals 4. I mean, I can show you many extra steps. There are about 4 steps of manipulating exponents that I'll need to get from here to there. But if you realize that these two questions are the same, then the solution should be the same, right?
Yeah, and that only works as long as you have 1 on top.
Well, I could have 3 on top, then I'll get 3 times 2 squared, so then I get 12. Okay? Yeah. So we can actually say this. I'm going to make a statement. Negative exponents in numerator give me positive exponents in denominator. And vice versa, if I see a negative exponent in the denominator, that becomes positive exponent in a numerator. So positive negative exponent in a denominator gives me a positive exponent in a numerator. So, for example, if I have something like 2 over 3 to the negative second power, like that. So I see a negative exponent in the denominator. I can move it to the numerator. And then there's nothing left in the denominator. So this becomes 2 times 3 squared over 1. So the negative in the denominator becomes positive in the numerator. So that's 2 times 9 equals 18. Okay?
So,
Well, yeah, let me show you all the math that you shouldn't be doing. So it's 2 over 1 over 3 squared, because 3 to the negative second power is the reciprocal. Right? So 3 to the negative second power is 1 over 3 squared, just by the definition. So that means I have 2 divided by 1 over 3 squared, which is the same as 2 times 3 squared over 1. So, you know, all those steps are, it's just too much busy work. If you just remember, if you take a negative power in the denominator, move it up. And if you have a negative power in the numerator, move it down. Okay? Let me just give you a little messier of an example. If I have something like this, 2 cubed times 3 to the negative second over 5 to the negative third times 7. Something like this. So 2 cubed in a numerator is 2 cubed in a numerator. I don't have to mess with that. But 3 to the negative second in a numerator, I can move it down. So negative in a numerator will become positive in the denominator. And at the same time, 5 to the negative third power, that's a negative in the denominator, I can move it up into the numerator, make it positive. While 7 is 7, doesn't go anywhere. So this thing is the same as 2 cubed times 5 cubed over 3 squared times 7. Whatever that equals to. Yeah. I mean, those properties allow me to do that. It just takes about 4 steps that I really, it's hard, it's easy to mess up in those steps. But just remember, if you encounter something like that, where you see negative powers, like this, well, or just in any place, like in the previous example, we had just a negative in the denominator, we just tossed it up. So here, if you have a negative on top, it goes on the bottom with a positive. And you have a negative exponent in the denominator, and it goes on top. On your homework. Again, these are, yeah. I mean, you'll find it. I'm not going to, it'll come up. So, but does that make sense? I mean, you can go ahead and compute whatever that equals to. I don't care at this point. I think it's, yes, 1,000 over 63. Yeah. Okay, good. And if I ask you just to make sure you're paying attention, 132.7 to the power 0 equals 1. Good. Just making sure. All right. So okay, so the big thing, that negative exponents are reciprocals. So these are our rules of exponents 7 and 8. Okay? Good? All right. So now, we've done these types of questions. If I ask you, what is the square root of 3 to the power 6? You will say 3 to the third, right? And how do we do that? You just divide 6 by 2. And 2 comes from the fact that it's a square root, right? Well, what do you think will happen if I ask you what is the cube root of 3 to the 6th? 2, because you will do what? Divide by 3. So it looks like you're taking the power and you just divide it by whatever the index is. Right? You agree with that? So really what you're doing, you're making it 3 to the power 6 over 3 equals that. Right? Well, that means you can have fractional exponents. In this case, 6 over 3 just worked out perfectly. But if I ask you what is 7th root of 5 cubed, well, technically that's, if you follow the same logic, that's 5 to the power 3 over 7. Right? You take the power, you take the exponent, and you divide it by the index, just like you did in the previous example. It worked out nice and pretty before. Here it doesn't. But, yeah, just leave it like that. But fractional exponents are radicals. Look at this. Let me show you something on the calculator. If I take a square root of 16, can you tell me the answer? 4, right? No problems there. But if I do this, if I take 16 and I raise it to the power 1/2. Now think about this, what I was saying before, right? The square roots or the radicals, you just divide the power by whatever the index of the radical is. So the square root has index 2, right? So same thing as taking the power of 16, which is 1, dividing it by 2, still getting 4. So basically, I know this is that didn't help. All I was saying that taking the square root of 16 is the same as raising 16 to the power 1/2. Because right now 16 has a power 1, and this square root has a silent index 2. So the same as 1/2 exponent. So, huh? Yeah. But I'm just going to give you this rule. That's rule number 9.
Or you can,
Yeah, go ahead.
so with the square root or 16 to the power 1, we're just getting that 2
From the square root. Yeah.
right there. We have something with
Well, here's the cube root of 27. Okay? Cube root of 27. What is the power on top of 27? 1, right? It's just 27 to the power 1. So what this rule suggests, that's a cube root of 27 is the same as to raise 27 to the power 1/3. We know the cube root of 27, right? What is that? 3. But at the same time, if I take 27 and raise it to the power 1/3, I'll get 3 as well. Okay? So fractional exponents are radicals. In general, so that's rule number 9. Rule number 10, if I have nth root of a to the power m, like that, that is the same as a to the power m over n. So m, the power, is the numerator. The radical is the denominator. Okay? So again, just rewriting, let's say if you have 3 to the power 5/7, whatever that is, this is the same as saying 7th root of 3 to the power 5. So the denominator is the index of your radical. The numerator is the exponent.
so 3
Mm-hmm. Now, I don't know what it equals to numerically. I'm just saying that that's the interpretation. The numerator is the exponent, the denominator is the index of the radical. Now, one thing here, that exponent, well, let me show you these two things. Do you agree that 3 to the power 5/7 can be thought of as 3 to the power 5 times 1/7? Is that the same thing, mathematically speaking? When do we multiply exponents? You have a rule, the third rule on the list, that results in the products. Yeah, so this is to say 3 to the power 5 raised to the power 1/7, right? In this case, you would multiply exponents. Well, now power 1/7, as discussed in rule number 9, the power 1/7 means the 7th root. So 1/7 turns into the 7th root, and 3 to the power 5 stays there. Now let me, well, I'm just trying to show you something else. But do you agree that this is the same as 3 to the power 1/7 times 5? Right? Because, 1/7 times 5 is the same as 5 times 1/7. So you following the same logic as 3 to the power 1/7 raised to the power 5, like that. Right? So that means what I have here is the 7th root of 3 raised to the power 5 on the outside. So it doesn't matter where you put that exponent, either under the square root, I'm sorry, not the square root, under the radical or all the way on the outside of the radical. It still means the same thing. Isn't that fun? So a general rule number 10. Yeah. Well, you know. No. You don't need that. Let me just give you that. That'll just confuse you. A to the power n over m. So, now how did I write it before? I wrote it. No, this is 9 and this is 10. So I had m over n. So m over n, just to be consistent. So again, all we have to remember from here is that the numerator is the exponent, the denominator is the radical. So there are two ways of expressing that. There's the nth root of a to the power m, which is the same as saying nth root of a raised to the power m, like that. These two are equivalent statements. So why that's kind of important is if I ask you what is the 4th root of 16 to the power 5, something like that. Order of operation tells you to raise 16 to the power 5 first, and then take the 4th root of that, right? Can you do that in your head? Can you raise 16 to the power 5? No. But this rule tells me that it doesn't matter where that exponent is, on the inside or on the outside. So I can say, well, this is the same as 4th root of 16 raised to the power 5. So now it tells you to take the 4th root of 16 first, which you can do in your head, which is what? 2, and then raise it to the power 5, which is 32. Right? What? Why? No, it's beautiful. Again, all you have to remember that the numerator is the exponent, the denominator is the radical. That's all you have to remember. All 4 and 16 turned into 2. 4th root of 16 is 2. So, and that's what we've been doing before with square roots. You were taking powers, dividing them by 2, right? Well, that's all it is. It's just taking number over here, dividing it by the number over there. Just like you did with the square root. When I asked you that question, you took 6 and you divided it by 2. Well, just sometimes when you divide numbers, it doesn't come out to be a pretty... No. No, this is just you taking the root. You're just thinking what number to the power of 4 equals 16. And that's 2. Okay. Good? So we learned 3 things already. We learned stuff about the higher radicals. We learned that negative exponents are reciprocals. The fractional exponents are radicals. Right? So that gave us 10 rules of exponents. Okay? Now, I have to fix one little thing in our theories, because if I ask you this question, again, don't write this down. You have plenty of that in your notes. But if I ask you this question, you would say just 5? Okay, a to the power 5. But usually when I gave you this question, I always said, assume that a is greater than or equal to 0. Look at the quiz that I just gave you. I mean, worksheet 17 that you just got back. There was a question on it. Question G, 4G on the second page. That I ask you, what is the square root of a squared? Assume that a is greater than or equal to 0. Right? I had to keep saying that. Assume that variables are positive, because things will get weird if I allowed non-positive variables in there. Because this is, again, was done by assuming that a is greater than or equal to 0. The reason why I had to say that, because again, the definition of the square root was, again, you have this in your notes, don't need to write this down, was this, right? Square root of a equals b means b squared equals a, but it also had that component. Square root of a has to be greater than or equal to 0, right? Had two components that the square roots always produce positive results. And actually, that's true for all even roots. All even roots will produce positive results. So again, if I ask you, what is the square root of 72 squared, you will say 72. And if I ask you, what is the square root of negative 13 squared, you will say 13. That's correct, right? So it's not just simply dropping the power. You also had to make it positive, right? Now, what is that operation that you might have seen before that turns negative things into positive things? Just by... We haven't done it in class yet, but you might have seen it before. This thing, what? Oh, you've seen it before. You graduated something before you got here. What am I miming here? Absolute value, right? The absolute value makes negative things into positive things. Have you seen it? Have you heard about absolute values? Right. Because this really becomes an absolute value of whatever's on the inside. That makes it positive 13. Now, what is the absolute value, by the way? Well, no, what is the, if I just talk about the absolute value as a concept? Yeah, absolute value, if I give you this absolute value of a, but what if a is negative to begin with? Yeah, but what if a is negative 5? Well, so then it does not equal a, right? No. But what is the absolute value? What is the real definition of it, conceptually speaking? How many of you have seen that thing that I just wrote on the board? Everybody, right? Everybody's seen the absolute value, right? So what does that mean? Yeah, that means nothing really. What is the physical interpretation of absolute value? Anyone? So if I ask you these two questions, you will have absolutely no problems computing them, right? Right? What is the answer in the first one? And what is the answer in the second one? But why? What does that mean? Yes. The definition of an absolute value is the distance from a number to 0. That's how far away a number is from the origin. So how far away is 3 from the origin? And how far away is negative 4 from the origin? 4. So the absolute value is really distance from 0. Okay, I know you knew that. So that's why I was giving you some hard time here. Now, here's what I'm going to start messing with you. I haven't been messing with you yet on absolute value. Now I'm about to completely ruin your confidence in absolute value, so get ready for that. Because you have absolutely no problems computing the absolute value as I wrote it. Right? These two examples, you have zero problems computing that. Figure that? This is the easiest thing we've done this whole semester. Compute the absolute value of 3 and absolute value of negative 4. Do you agree with that? Now, really think about how does your brain process that operation. If you were a calculator, if you were a very cheap calculator, that can only multiply, divide, add, and subtract, how would you compute the absolute value if you are only capable of doing those 4 operations? Because really, we're living in the... Yeah, but times it by negative 1. That's what you would do. Yeah, but you would not just automatically times everything by negative 1. You would actually analyze the input first. You would say, if the input is positive to begin with, I'm not going to mess with that at all. But if the input is negative, I'll multiply it by negative 1. Right? So the official definition of an absolute value is this. There are 2 things happen. That absolute value of a number is that number if that number was positive to begin with. So if absolute value of 3, that equals 3, because 3 is positive, so don't mess with it. Absolute value of 12 is 12, because 12 is positive. Don't mess with it. Well, that would be just, don't even times it by anything. That was it. But if it's negative, you will multiply it by negative 1. So if A is the negative number to begin with, in order to make it positive, multiply it by negative 1. That's how you turn negative things into positive. Right here, negative. So this is really the official definition of absolute value. And I'll come back to that in a second, where we actually have to use it. Because, of course, you really don't need that to compute this too, right? And this is how you're going to be computing absolute value of negative 4. That's just 4. Okay? You're not going to be, I don't want to see you multiplying by negative 1. I mean, I understand that you have developed past a cheap calculator where you can just drop a negative sign. That's really what you're doing. You're just ignoring the negative sign. Now, the reason why we're bringing up the absolute value, because officially, the square root of a squared equals absolute value of a. That's what a square root of a squared is. That guarantees that it always comes out positive. Okay? So from now on, I won't be saying assume that a is positive. So I will write things like this, simplify square roots of 25a squared. You will have to write 5 absolute values of a. That will guarantee that the answer comes out positive. Yeah. Now we're going to start getting a little messy. And that works for all even radicals. With odd radicals, anything goes. So here are the 2 major rules. If n is odd, then nth root of a to the power n just equals a. We don't have to worry about that, because odd powers can end up with negative answers. Nothing bad happens. But if n is even, then nth root of a to the n is absolute value of a. That guarantees that the answer comes out positive. Okay? So you have to make sure that no matter what value of the variable is, the result after doing any even radical has to come out positive. So the absolute value guarantees that. But what we need to learn now is to how to compute absolute value. And of course, it seemed like you're doing pretty well with the absolute value of 3 and the absolute value of -4. You had no problems with that, right? Okay, let me give you a few more examples. Just computing absolute value. So how about that one? 10, right, good. You didn't have to work very hard for that one, right? We like that. How about absolute value of square root of 5 minus 2? So, no. Can I just ignore the square root? No. Well, square root of 5 minus 2 is some number. Do you agree with that? Square root of 5 minus 2 is some number. No. Square root of 5 minus 2 is very different from square root of 5 plus 2. Difference is 4. But do you all agree at this point that square root of 5 minus 2 is just a number? Right? It's some irrational number, but it is a number. How do we take absolute value of a number? If it's positive, we'll let it be. If it's negative, we'll multiply it by -1. So you have to ask yourself, is square root of 5 minus 2 a positive number or a negative number? It's positive, because square root of 5 has to be bigger than 2. Do you agree with that? So something bigger than 2 minus 2 is what? Positive. And how do we take absolute values of positive numbers? Positive numbers. How do we take absolute values of positive numbers? By doing nothing. So then it just square root of 5 minus 2. Because square root of 5 minus 2 is a positive number. So the absolute value of a positive number is that number itself. Right? Just like the absolute value of 3. 3 is positive, don't do anything, equals 3. Square root of 5 minus 2 is a positive number, don't do anything, equals square root of 5 minus 2. Does that make sense? What if I ask you? Well, I know that square root of 4 equals 2, so square root of 5 is bigger than 2. So bigger than 2 minus 2 has to be positive, right? How about this? Absolute value of square root of 2 plus square root of 7. So that means what? Do nothing. Square root of 2 plus square root of 7. Because square root of 2 plus square root of 7 is a positive number, because it's a plus in between. It has to be positive. So the absolute value of that is the same number. Does that make sense? It's just doing nothing. But you have to realize that the number on the inside is positive. So the absolute value of a positive number is that same number. You don't have to do anything with it. Does that make sense? Okay. Square root of 2 minus square root of 7. Uh-oh. Do you all agree that square root of 2 minus square root of 7 is negative? Now, how do we take absolute values of negative numbers? -1. So we're going to take this thing multiplied by -1. Right? That's what that rule told me to do. If your number is negative, in order to just change the sign, times it by -1. Now that actually, I can do something here. I can go all the way back to us messing with rational expressions. This is same as just flipping that expression as square root of 7 minus square root of 2. Remember when we were flipping, that was giving us a negative? So that's the same thing. And let me show you this on the calculator. If I plug square root of 2 minus square root of 7 in my calculator, I'm getting -1.23, blah, blah, blah. So what is the absolute value of that number? Yeah, but if I do square root of 7 minus square root of 2, I'm getting 1.23, blah, blah, blah. So you see, all I have to do really is to flip it around the negative. That will change the sign. Isn't that fun? It's going to be negative. How do you make it positive? Or just flip it. So it's square root of 5 minus 2. So if it's positive, don't mess with it. If it's negative, and this is really the only case where you have to stop and start worrying about the absolute value when the numbers are nasty like that. So if it's negative, you just flip it around to minus. That'll make it positive. But it'll be the same number. So you thought the absolute value was easy. But again, it all comes down to what's on the inside. Because that's all the absolute value does. It makes sure that the answer comes out positive. So if you start with a positive thing, you don't need to do anything with that. You just leave it alone. So square root of 5 minus 2 is positive, so don't mess with it. Because if you start messing with it, if you start changing minuses to pluses, you're going to get a totally different number that's a different distance from 0 than whatever you started with. But if you start with a negative number in order to make it positive, just flip it. Wasn't that fun? Taking absolute value can be tricky. Any questions on that? All right. Okay, good. Now that took us a while to get through everything today. Okay.